Yeah, thank you for the introduction, and thank you to the organizers for putting together this very nice conference. It's been great. I should start by saying that this is joint work with my co-author, Jessica Stewart Kelly, who's from Christopher Newport University in Virginia in the US. And hopefully most of the title is somewhat clear. It's this last part that might be confusing, right? This exceptional Laguerre differential expression. And so you may not have seen these before. By exceptional, I mean it's associated with some kind of exceptional orthogonal polynomial. So I should explain a little bit of this too. So these exceptional orthogonal polynomials are complete systems of orthogonal polynomials that satisfy a Sturm-Liouville problem. The big catch is that they're missing a finite number of degrees from their sequence, and yet they are still complete within this modified Hilbert space in some way. And so there are isolated examples in the math physics literature dating back to the 90s through 2010 or so. But this was first really rigorously mathematically described in two papers by Gomez-Ulate, Kamran, and Milsom. And this was 2009, 2010. And so all of a sudden there was a lot of interest in these objects and study of their zeros and recurrence relations. This was very strange in some way. The authors were mostly motivated by two things. They wanted to have some applications to quantum mechanics, which I'll talk very briefly about in a minute. But also they wanted to extend the classical Bachner theorem. So if you remember, the classical Bachner theorem says that if you have a second order ODE with polynomial coefficients, and you want a complete orthogonal system of polynomials, there's only three options really, up to a complex linear change of variable. And it's Hermite, Laguerre, and Jacobi. And you can roughly think of this as, if you're interested in self-adjoint extensions, that the deficiency indices are either 0, 0, 1, 1, or 2, 2. Today we're going to focus on Laguerre, of course. And so they wanted to extend this Bachner problem to, instead of considering polynomial coefficients, to consider rational coefficients. And this sounds very easy, but it took a lot of time in the literature to develop this theory. And so finally, this last paper actually proves this extended Bachner conjecture, and this was very recent, maybe 2019 or so. It didn't appear for a year or so, so maybe it's 2020. And so this says if you have rational coefficients, then you really only have three types of answers to this question as well. It's Hermite type, Laguerre type, or Jacobi type. And they're called type because they're related to the classical systems in some specific way. And that's what we're going to explore today. So like I said, we're going to focus on Laguerre because these deficiency indices are kind of 1-1, and it's a first step of trying to analyze this spectral theory here. Okay, so how does this connection work? Because this is what we're going to exploit, of course. We know a lot about the Laguerre expression, but not about these general XOPs. So yeah, I'll abbreviate this by XOP when I'm talking. This connection is made via Darboux transforms, and of course these are involved in a lot of different areas of mathematics. In this context for Sturm-Liouville equations, it's explicitly given by Darboux-Crum transformations, and so this dates back to maybe the 1930s, I think. But in essence, this is what you have. So I'll let cursive L be a classical expression, Laguerre for us, of course, and this mathfrak L will be some exceptional expression. And then you can make a rational factorization. Of course, these are very non-unique. There's a lot of different kinds that you can do with this. And there's very little requirements imposed here. What we're going to really exploit is because we want to have spectral theory, you still need information about the solutions. Fortunately, this rational factorization gives you a lot of information just by having this exist. So you have this intertwining property. Basically, if you let y be an eigenfunction of the classical expression with eigenvalue lambda, you can just apply both sides of this equation to y, and you see that ay is now a new eigenfunction. So this is very nice. And so we'll exploit this heavily. Now, like I said, I don't really want to give you all the details of this Darboux-Crum transformation because these exceptional expressions drag out very long. Instead, I'll tell you that really it boils down to just expressing a bunch of eigenfunctions into a Wronskian, okay? So quasi-rational eigenfunctions just mean that the eigenfunction itself is rational and its log derivative is rational. For the Laguerre, classical Laguerre expression, there's 4 types of these. And so you have 4 types of seed functions to put into this Wronskian, and then you kind of generate an XOP expression in this way. Okay, so now I can say very slightly a little bit about the quantum mechanical impact of this and why people are interested in these from the math physics literature. So they're eigenfunctions of exactly solvable potentials, but in particular, they're eigenfunctions of rational extensions of these potentials. And so they get you a new class of, if you're interested in exactly solvable stuff, you can solve more things, of course. And so there's three operators listed here: harmonic oscillator, isotonic, and trigonometric DPT potential. So the one that corresponds to Laguerre is, of course, this isotonic. And so if you want to look at rational extensions of this, one of the natural objects is exceptional Laguerre polynomials then. But also, these Darboux transformations come into supersymmetric quantum mechanical partnerships. They're often called like this. They're often expressed in different ways, so I'll be very careful about saying this. And then, of course, there's many other implications here, but these are really just papers where XOPs appear in the math physics literature. So they're useful in many contexts, but I don't know these very well, to be fair. Okay. We want to do spectral theory, so I need some other kind of tool. And my favorite tool in this context is always boundary triples. And there's a lot of experts in the field and in the audience, so I boiled this down to a very specific scenario just for our purposes. We know we have defect indices 1, 1, so this is very simple. Sturm-Liouville expressions are, you can find boundary triples very easily. Essentially, you have two maps, gamma 0 and gamma 1, and then you have some boundary space. For us, it's just the real numbers, maybe with infinity or something. And these maps need to have two basic properties. They need to recreate the sesquilinear form. So by this, I mean it's essentially the inner product of LF comma G minus the inner product of F comma LG. You're kind of measuring how self-adjoint functions are against each other within the maximal domain. And then on the right-hand side, these inner products are just an R, so this is very easy. Essentially, this should recreate integration by parts for Sturm-Liouville operators in these explicit expressions. And then they should be surjective onto the ranges to make sure that you actually capture enough information about the defect spaces. So why do we want to use this in this context? Well, there's a few nice things. Number one, they give you a natural parameterization of all self-adjoint extensions via this one parameter family introduced by boundary triples. So you see that all extensions are basically given by theta gamma 0 equals gamma 1. This is very nice. The other thing we can exploit is that once you set up these boundary triples, there's a nice theory to actually just produce a Weyl M function, basically. And so we can, after we create this and satisfy some initial conditions with our fundamental solutions, this Weyl M function is basically just going to be produced from the machinery of it. And so we don't have to work so hard for this. And we'll have a lot of these explicit things coming later. Okay, so I can finally formulate the actual goal now that we've been talking for a few minutes. We would like to find an explicit Weyl M function and then actually get the spectral information out of general Laguerre XOP expressions. And there's a lot of things to say here. So in terms of Darboux transformation, I mean, I would like to be able to have you be able to give me some collection of seed functions, put them in a Wronskian, and generate some Laguerre expression. I would like to be able to tell you, just based off the seed functions you give me, what the spectrum of that, the spectrum of any self-adjoint extension for that operator should be. And so the spectral theory of XOPs has been investigated for the last decade or so. I think this goes from 2012 all the way up to last year, 2021. And there's a few differences here. So most of these papers look at very specific operators. And so you're interested in one class of XOPs, one set of them, maybe. Of course, today we're going to try to handle all of Laguerre-type in one fell swoop and try to answer the question. But also, they're only interested in usually one extension, of course, because among all of these self-adjoint extensions of this one parameter family, one of them will produce Laguerre XOPs, and that's it. And so people are interested in this extension because then you can extract other information, of course. Now, from my perspective, the Darboux transform is actually very interesting here, because in the math physics literature, this is often referred to as a state-deleting transformation, which on the surface seems to be apt, because you have some sequence of polynomials and you apply a Darboux transformation and you knock out one or a finite amount of them. And so it state deletes in some way, right? But if you're looking from this expression of all self-adjoint extensions, those eigenfunctions go somewhere, of course. And so I'm more interested in how do they interchange between all the extensions and the balance that goes on between this process. The last thing was that we know our spectrum is discrete already. So you have one extension that's a complete system of orthogonal polynomials. You have discrete spectrum. And then you're rank 1 away from everything else. So you're discrete, okay? And so for a decent amount of time here, I'd like to basically just go through an example. Of course, if we're dealing with these general expressions, things get very complicated very quickly. And so I'd like to just demonstrate the procedure with an example and try to get us settled a little bit. So this example is actually kind of known. It comes from this paper here of Liao, Littlejohn, Milson, and Stewart Kelly. And so they find the spectrum of one particular extension, and we'll reproduce this kind of as a sanity check, and then find all the other extensions as well as a byproduct. So here's the general procedure I would like to perform. You start with two linear independent solutions of your classical expression, and then you exploit this intertwining property of the Darboux transformation to get new solutions, okay? Everything will be explicit, of course, so this is fine. Then you can build some kind of standard boundary triple from this theory. And I'll skip these two steps right here for a second. And then you find a Weyl M function, you extract the spectral information. This should be relatively straightforward. Now, in the general procedure, what's actually difficult is this 3.1 and 3.2. So if you start with, you hand me this handful of seed functions, I need to sort them in some way to extract information. And this is where a lot of the techniques actually come in. So we need to rewrite these in some kind of standard form and then make sure that when we generate this fundamental solution, do we actually satisfy these initial conditions which are somewhat hard to satisfy? So in the example, of course, you won't see these steps very much because everything's explicit. So I'll warn you about this. I'll put some general stuff up at the end, but it gets a little complicated. Okay, so this is the type 1 Laguerre XOPs with codimension M. So basically what this system is it possesses a complete set of orthogonal polynomials, but they're missing degrees of zero through m-1, so m degrees total. So that's why we have an m subscript here. So this is the classical Laguerre expression. There's some kind of rational factorization given in the literature. This was kind of the first discovered one for Laguerre, so it's type 1. And this is our new expression, and it's basically just, the inversion of this. So this is all from the rational factorization. And the appropriate weight function, you can see it's not the normal Laguerre, it's divided by this Laguerre polynomial. And so immediately you should check what I've been telling you, that this Darboux transform really should be a Wronskian, right? The function put into this Wronskian is exactly the seed function. Okay, you have to take care of this alpha minus 1 to make sure it matches up. But you can see there's an f prime and an f. This is really just a Wronskian, okay? It's the simplest kind you could possibly have. So it's a good example for us. Now, we have this operator now. We can find a maximal domain. It's very simple. You want some minimal conditions to define derivatives, and you want to map from L2 to L2. Of course, we have this sesquilinear form. Again, this is basically just what you get from integrating out by parts. This is Sturm-Liouville stuff, so it's all very explicit. And because it's explicit, we can define some quasi-derivatives. Here they're written as gamma 0 and gamma 1, because I want to build a boundary triple, right? And you can think of this as basically pairing certain particular solutions inside of this sesquilinear form against general functions. So here we have two different functions, x to the minus alpha, and this is really a constant, right? This is just the seed function evaluated 0 with some normalization attached to it. So this is basically LF equals 0 with some normalization attached. It's very clear. It's done in a slightly strange way, but you can just multiply this out and show that this makes a boundary triple because it recreates this Green's identity, and everything's very explicit. Okay, so I have to give you the solutions for the Laguerre expression to start with, and then we'll put this through the Darboux transform, of course. So solutions of the Laguerre expression are given in confluent hypergeometric functions, which sound very bad, but they're basically power series, okay, with different kinds of coefficients. So there's two solutions here. Of course, we're working with alpha minus 1 we saw on the previous slide. And this first solution basically produces all of the classical Laguerre polynomials. It's a power series. When lambda equals the natural numbers, it terminates and you get a polynomial. And then you normalize it in some way. The second solution is not usually applied in a lot of the literature, but it's a Laguerre function of the second kind. It has some kind of blow-up behavior at 0, and this is what makes you limit circle at 0, and why you need a boundary condition in general. Okay, so we're going to say that we put these functions through our Darboux transform. I'm not going to show you the details, of course, and then I'm going to apply some kind of normalization constant, okay? Again, I'm going to sweep all of this under the rug, even though it takes a few pages, but it's all explicit. And you end up with a bunch of gamma function stuff here, okay? The initial conditions we really want to satisfy for boundary triple theory is given right here. These are basically quasi-derivatives of these new solutions should satisfy some initial conditions at 0. And then all that's left to do is produce an M function and analyze the spectrum, right? So the way you produce an M function in this context is you take a general deficiency element, which is really just a linear combination of these previous solutions I showed you, of course. And so here, this is given by the trichotomy confluent hypergeometric function. You get two natural self-adjoint extensions from this boundary triple theory because you define two maps, gamma 0 and gamma 1. You can take the kernel of either of these, and this is just a self-adjoint extension. Here I've mixed them up because we have other applications in mind. So L0 is really gamma 1, the kernel of gamma 1. L infinity is the kernel of gamma 0. Okay, and I claim that you can apply this Darboux transformation. It's a Wronskian, so you can just apply it to each individual solution, and then you apply these normalization constants. You see the C and D popping out here, and this is enough for us in some sense. And I can give you explicit Weyl M functions now. So this first one is the extension not known in the literature already. And so you have some ratio of gamma 1 and gamma 0 applied to this general new deficiency element for the XOP operator. Now, the gamma function has no zeros, so 1 over the gamma function is analytic. But the gamma function does have simple poles at negative integers. So any spectral information, you can read off this M function. If you find simple poles of the M function, your extension has simple poles at those points. So all of the spectral information basically comes from this gamma of 1 minus alpha minus lambda term, and that gives you this sequence of eigenvalues right here. You do have this extra term from the denominator of lambda plus m plus alpha, and that gives you this extra eigenvalue. And so from the classical perspective, this is very strange already, because this is exactly what you would expect from this similar extension in the classical situation. You would get exactly this sequence, but where did this come from, basically? And that's the Darboux transformation, of course. So you have an M in here, and M hasn't appeared in many of our formulas yet, but it's the number of codimension for this exceptional expression. The M function that was kind of known, it was, this is the extension that produces your type 1 Laguerre XOPs. And so the spectrum of this extension was known from this paper I mentioned already. And you don't see this expression. I mean, you see it, but it doesn't do anything. And all of your spectral information comes from this gamma of minus lambda. It's very simple. Okay. So now I can say a few words about what are we going to do in general, because this was an easy situation for us, right? I told you the main obstacles were basically classifying these sets of seed functions and then actually normalizing them in some way. So of course we can do all self-adjoint extensions, but I'm going to skip through some of this stuff. This is just to show you that we can explicitly handle every situation possible. Okay, so here's the general situation. I said there's 4 kinds of seed functions. You can kind of collect these in some way. We're going to put them into a Wronskian, so we don't want to repeat any of them, because then the Wronskian is going to be 0. You can actually do this, but it's the classical situation then. You don't have anything different. And so basically you get 4 decreasing sequences of indices based on these different kinds of seed functions. And they're collected here in terms of Maya diagrams, which you may not have seen before. So I'm going to give you an example on the next page of how these actually work. And again, I would prefer to work with examples because this is much easier to see. So here's just some Maya diagrams that we picked. They do satisfy some basic conditions that are in the paper, but are a bit technical. So here you have a null set on the left side and 3, 2 on the right. So these Maya diagrams have filled in boxes on the left of the origin. There's some origin delineated here. And then they should have filled boxes on the right side at those points, 3 and 2. Everything else on the right side should be empty. And it's kind of the opposite with this M2, okay? So everything on the right side is empty. You're going to make the boxes on the left empty if minus this number, minus 1, is included in this index. So 1, 0 goes to minus 1, minus 2, and these are left empty in some way, okay? And so these are the kinds of seed functions actually we're describing. I told you one of the main obstacles was how do we sort these into a standard way? Well, there's a whole theory of Maya diagrams and partitions, of course, and so you want to shift this. You can imagine fixing the origin and shifting all the boxes left and right in some way until you get, instead of 2 sequences, you want to get just 1 now. I would like to collect all of these finite indices on one side of this thing. And then we can work with partitions instead. So there's a canonical form for Maya diagrams, which basically says that all of the boxes to the left of the origin should be filled, and the first box to the right should be empty. And so you see this M1 already satisfies this, we're fine. And so we don't need to shift, so T1 is 0. T2, on the other hand, does not have this property. It needs to move to the right 2. Okay, so T2 is 2. The other thing you would like to do is conjugate canonical position. We do this because we have two types of solutions we're putting into these Wronskians, and it's a bit technical. But it's exactly the opposite. So you would like everything on the right of the origin to be empty and the first box on the left to be filled then. And so neither of these satisfy this. The first box on the left to be filled would shift all of these to the left basically by 4, and that's why T1 prime is 4. Okay. So what does this mean? I mean, it's fun to work with pictures and stuff, but what does this mean for the differential operator, and what does it mean for the eigenfunctions? Well, in general, these are your solutions. It's the same ones I showed you previously. Alpha is not -1 anymore. And you have to apply some kind of appropriate prefactor to work with these objects. Basically, this just turns it into a polynomial. And the first thing you should say to me is, Dale, why do you have two polynomial solutions? One of them definitely was not polynomial. But the answer is basically that after you apply these shifts, you kind of know what L2 space you're supposed to end up in, and you can multiply by its behavior later. It doesn't actually affect any of our constants. Okay, so we have a bunch of seed functions in a Wronskian basically against one of our solutions, and this looks the same as the previous examples, okay? So this shifting procedure that I was describing basically looks like this from the math point of view, okay? So you try to look for certain situations where you have a filled or empty box right beside the origin. And what that means is your index was 0, so you have like L sub 0. The 0th Laguerre polynomial is 1. And so your Wronskian can be made easier, right? You just pull this one out, you expand upon this, and then you put some terms back in if you have to. And so by doing this, you slowly shift the Maya diagram one way or the other. And if you're not in either one of these positions, then you can add 1 or -1 and do the same exact thing. You have to be in one of these situations. Here, none of this really matters. All we're interested in is following this lambda term, because this affects our spectrum, of course. And we want to follow this alpha plus 1 because this tells us what space we're going to end up in eventually. We have to find an appropriate weighted L2 space, of course. Okay, and if you apply this many times, it gets very complicated. So this is an opportunity to exercise your patience, I guess. But you get a whole bunch of stuff that pops out. You shift M1, you shift M2, and then you get a bunch of other stuff that doesn't depend on lambda. For our purposes, none of that matters. If you have an example, these produce very nice, clean methods, actually, though. And so you can see here that you have some term, some dependency on lambda based on whether you shift to the left or to the right. And this is true for M2 as well. This is also only for canonical position. We have to shift everything into another one, too. And so it gets a bit complicated. Again, another slide where you can ignore 95% of this. My argument is that once you have these solutions shifted into a canonical position, you don't actually need to worry about most of the terms in them. So you're taking Wronskians with a bunch of polynomials and then a power series solution, basically. If you're going to apply some kind of quasi-derivative like this gamma 0, gamma 1 I showed you previously, most of those terms just go to 0 because they have powers of x in them, okay? We're going to 0 anyway. And so what we really want to do is actually just evaluate this Wronskian at 0. And you can do this basically by shifting, it's a Wronskian, so it's a matrix. You pull out a bunch of stuff from each row and column, and you try to make a van der Monde determinant. And that's what this is not the Laplacian. It's a van der Monde determinant. And basically that means you take each of these entries and you take their difference and multiply them all together. Okay? But this also produces a lot of dependency on lambda. This is the only lambda on this whole slide, basically, or these two. Okay. So I'll show you what happens with these Maya diagrams I picked in the example earlier, okay? Because none of this is known in literature. I think the most people had done was 2 entries in a Wronskian before this, and now it makes it very simple to do all of them, basically. And so M infinity corresponds to L infinity. This is the extension that doesn't have any Laguerre polynomials in it. And you see some interesting stuff happen. So you have the same kind of term we saw previously. You get minus lambda minus alpha, and this produces these guys. But some of them cancel out, right? Lambda equals 3 and 2 are also eigenvalues. And the poles of this function actually cancel with these two functions here. So you don't have a 0 term. And I've shifted the index up 1, so you can't really see it. This extension has the Laguerre-type polynomials in them, and the spectrum is pretty similar. All of the work is really done by this minus lambda term, the same as in our previous example. Some of them cancel out, the 2 and 3, and you get these extra eigenvalues popping out here. And so for our perspective, this was very interesting because you actually get to see the interplay and what the Darboux transform really introduces, how it takes stuff away from certain extensions. And you can try to play this game of, if I want to make certain eigenvalues be produced from this procedure, you can try to make that happen. Yeah. And I think I'm pretty much out of time, but I'll mention one key paper that, this paper of Banu and Kujalars. So I'm not from the exceptional orthogonal polynomial community, it's a whole community. But we relied heavily on this paper to help with these partitions and the Maya diagram procedures and stuff like this. The spectral stuff I could handle, but this is a little bit different for us. And so here's some other stuff I mentioned as well. Okay, and that's it. Thank you.